Hello there, this is Alana Tuckey, and this is going to be the lecture for section 7.7, which is Finding Quadratic Models. This is going to be a particularly important section for your second project in Math 131. All right, so let's look at example 1. Let f of t be the average annual expenditure in thousands of dollars for people in the U.S. at t years of age. So we have the different age ranges right here, and then we have the average annual expenditure in thousands of dollars. And this is going to be the number we're going to use to represent that age range, because we can't say 25 to 34 in a calculator, but we could say the number 30. All right, so let's consider a scattergram of the data. Is it best to use a linear, exponential, or quadratic function to model these data? Explain. Well, there's the scattergram, and so rather obviously a quadratic would be best. Because the data form a parabola shape. In other words, they data go up and then back down. Now, not all quadratic models will actually follow that pattern, but if they do follow that pattern where it goes up and back down like this, then you better use a quadratic model. All right, so now we're going to find a quadratic regression model for that with our calculator. So let me grab the calculator. I go to Stat, Edit. I'm going to clear out my old data. I'm going to type in my new, so 20, 30, up to 80. And there we go. And now I got to type in the next numbers. So 28.1. So go to the right, 28.1. And so on. All right, I'm going to pause you and I'm going to type in those numbers. All right, there they are. They're all in there. Okay, so now, just like the other regressions we've learned in this course, you go to Stat, you go to Calculate, and number 4 is what we used in Chapter 3, and then number 0 is what we used in Chapter 4 and 5, but now we want a quadratic regression, which is number 5 right here, quadreg. So grab that. You want to tell it that your X list is L1, your Y list is L2. If you'd like it to store a regression equation for yourself, then you can. Not necessary, but just a reminder, you'd press variables, move to the right to Y variables, pick number 1 function, pick number 1, if you so desire. That's optional. Always leave frequency list blank for our course, and then go down to Calculate and press Enter, and there it is. All right, so now we have to type that up. So let me go grab that and type it into my lovely notes here. There we have it. So f of t equals negative 0.032 t squared plus 3.154 t minus 20.721. And there's our regression equation. All right, so how can we verify whether this model does a good job of fitting these data? Well, you could graph it on the same graph that you did your scatter plot, right? Okay, so let's take a moment and graph this. Now we already have the equation right here in y equals. So if I press y equals, I can see the equation sitting there. The negative 0.03 x squared is in the front. That's because I stored my regression equation. Remember when I went Stat, Calculate, number 5, and under here, under Store Regression Equation, I picked variables, move to the right to Y variables, pick number 1, press Enter, Enter. And when it runs the regression, it automatically stores the regression equation for me. Then I also want to have the scatter plot on, so I want to go up to plot 1 and press Enter. That way it's nice and dark, and that'll turn on the stat plot. And then to make a window, I press Zoom, and see at the bottom, Zoom Stat, number 9. So if I hit 9, it'll make a window that automatically fits my data. So there's the data, and then there is the regression equation. And I can see that it's doing a really good job of matching those points. So I'm going to draw a picture of it on my paper. Well, I'm just going to copy and paste. You're going to draw a picture. So you draw a quick sketch and say, we can verify the model is fits the data because it comes close to all the data points and does a good job of fitting these points, right? So it's coming close to all of them. It's fitting the general shape of the data points. It's not going to go through all the data points. That's not how it works, but it should come close-ish to all the data points, which it does. I guess I should say and or. And or does a good job because it's the same idea, right? It's doing a good job of fitting the data points graphically. So we can verify that it fits them well using a graph of the points and the regression model. There we go. The model comes close to all the data points. There we go. Okay, so again, just to reiterate, we verify that the model fits the data well by using a graph of the points and the regression model, and the model comes close to all the data points and or does a good job of fitting these points. Sorry, that took a little bit to get that out. All right. This next page is just calculator instructions, and then how I graphed those things in Excel, which you'll need for your projects possibly. All right, let's get down to here. This is a recap of all the regression you've learned in the course so far. So in Chapter 3, we learned about, and Chapter 2, we learned about linear regression. So that was of the form mx plus b. So L of x equals mx plus b. That's best for pictures like this, where you have a general decreasing trend by a similar amount every time, or an increasing trend, right? So it's steady growth or steady decline. Steady growth or decline. Let me put that in somewhere. Hold on. There we go. So steady growth or decline, that's linear. But there's a problem. If you're going to extrapolate pretty far off away from your data, you're going to end up in trouble because a line will eventually hit the x-axis, and that'll cause you to have negative predictions, either far into the future for a decreasing line like this top one over here, or way in the past like this increasing line over here, which would match this bottom graph over here. So you're going to have negative values, and those negative values don't make a lot of sense in the long run. So you got to be careful with extrapolating too far with a linear line. All right, then what about exponential growth? Okay, so exponential, you have growth and decay, if you recall those two basic types. So this is decay right here, and this is growth over here. Growth. Okay, so exponential growth, exponential decay, very useful things. However, it's hard to see, but exponential curves are extremely steep, and it doesn't take too long to get to that very, very steep portion, which can make some pretty crazy predictions that are way beyond what could actually happen from the real data. So you got to be careful with extrapolating, going too far into the future or too far in the past, because sometimes exponential curves just don't make a lot of sense if you get too far away from your actual data. And then the quadratic. Now, ideally, a quadratic will have this lovely shape, but they don't always have to have that shape. Sometimes you can be looking at half of the parabola, right? So if I cut off this parabola halfway through and just looked at that bottom portion, that would be a quadratic as well. But again, just like before, you can make some pretty crazy predictions because the parabola, because of its shape, will have it so that you're going below what makes sense far in the past and then again in the future. So it'll kind of dip down and then back up and then back down. And a lot of times the tails don't really make a whole lot of sense for quadratics. So you got to be careful if you're getting too far away from your actual data, if you're extrapolating. All right, so what are the best ways to check which model is your best fit? I mean, if we have these three different types, how can you tell which type you're looking at? Well, the first thing we've looked at is scatter plot, this middle column here. You kind of look at the data and try to see, which model would do the best of coming closest to all the points. Okay? And then the next thing you might want to do is which model has the r² value closest to 1, right? And then beyond that, you can ask yourself, well, maybe it looked like the exponential was doing okay, but then it came up with crazy answers, so I'd rather use the quadratic instead. In other words, which model does the best job of extrapolating past the data points? And that's kind of a tricky situation. All three of these are kind of tricky. There's no one right answer for what the best model is. Sometimes it's a judgment call between whether it's quadratic or exponential, or linear or exponential, that kind of thing. So you're going to have to make some judgment calls. But before we go much further, let's talk about what r squared is. R squared is called the coefficient of determination. It's a number that's between 0 and 1 that gauges how good a fit the model is for the data. The closer it is to 1, the better the model, roughly. Now, there's a lot more that goes on with r squared, and we are not going to get into it in this course. We just wanted to give you just a tiny taste of r squared. So the r squared value is something that your calculator will find automatically if you do something. So you have to turn on, and let me find it. So you hit second catalog. It's above your 0. And you want to scroll down. Actually, if you hit alpha D, you might have to do it again. Alpha D, it'll put you in the D's, and you want to go to diagnostic on. So kind of use your arrow key and keep going until you find diagnostic on. You'll only have to do this one time. You will never do this again. This is a one-time only deal. Up there it was. Come back. I pressed the up arrow too many times. There it is, diagnostic on. So you hit enter, and then you hit enter, and it'll say done, and that's it. You've done it this one time. You don't have to do it again. It's fine. So now every time you run regression, let me show you. If I run quadratic regression again, fine, go down to calculate and hit enter, you'll notice when I ran it on the first time, my calculator gave us this r squared value. See it right there? R squared, that's 0.9704. So our r squared was 0.970, roughly, because it says to give 3 decimal places. So it's an approximation because it's a decimal that has no end and all of that. Just like pi. It goes on forever and ever and all that good stuff. Although actually it's a rational number. All right, so what does this tell us? Well, the quadratic model was a good fit because r squared is very close to 1. In general, you want your r squared value to be above 0.64 or so. Being above 0.64 would be a good, so we want r squared above 0.64 for a strong relationship. And again, there's a whole lot more to r squared. That's all a statistics course, which we are not going to deal with too much in this algebra course. But just suffice to say that the higher your r squared value is, the better it is for you. And actually, once you've turned this on your calculator, it'll actually run r squared every time you run a regression. So let me show you. Here's a linear regression right here of that same data set that we had. And I press calculate, and I can see the r squared value. Look at that. It's really small. It's see the e over here? So it's 0.00004. Extremely tiny because that data was not linear, right? And then I do stat calc, and then I can run the other one we've learned, which is exponential regression. Right here. And it wasn't exponential either, but when I run the regression, it'll find r squared now. Every time. And see, again, it's super, super tiny. That's because our data set, if you recall, was this data set, this picture right here. There's no way that's exponential or linear. And that's why you're coming up with terribly small r squared values, right? Because these are r squared values that are extremely close to 0, 0.00099. Very, very tiny. We want an r squared value of at least 0.64. Even the 0.5s and 0.4s would be okay. Not great, but okay. But this is terrible stuff. Okay, that's it for introducing r squared. I'll see you back here next time for this second example right here. See you then.